Hi, we are G-Force, and our team is Lindsay Weingard, Vincent Chen, Fong Li, and Long Win, assisting in gastronomy tube feedings. Amyotrophic lateral sclerosis, ALS, is a progressive neurodegenerative condition that leads to the deterioration of motor function due to the loss of motor neurons. When ALS patients begin to experience dysphagia, or difficulty swallowing, some opt for a gastronomy tube, or a G-tube, which is a device that is surgically inserted into the stomach to assist with liquid feedings. In order for a G-tube to be effective, a technique commonly referred to as gravity drip is utilized, which occurs when formula is hung from an intravenous bag at a height of 46 centimeters above the stomach so that gravity can allow the food to travel from the IV bag to the patient's G-tube, then stomach. 5,000 people are diagnosed with ALS yearly, and we want to provide a way to set up their feedings without relying on the assistance from caretakers or family members. Problem statement. Patients with ALS have upper extremity weakness that makes it difficult for them to raise the feeding bag to the necessary height for gravity drip. Additionally, they are often home alone and cannot rely on the assistance of family members. Current solutions do not allow for personal autonomy because they cannot raise the feeding bag to the appropriate height. Design criteria. Our most important design objectives were ease of use, which is defined by user-defined scale, and easy maintenance. The constraint on this project were water resistance, which resists spills up to 1 liter, and the ability to raise the 1 kilogram IV bag of formula to 46 centimeters above the stomach.
This is our assisting gastrostomy tube feeding device, and as you can see here, I've simulated having a gastrostomy tube, and it's attached to this IV bag. Our design is for patients with ALS who are too weak to raise this bag up by themselves. So here at table height, where they have enough mobility and strength, they're going to open the IV bag, and then from here, they are going to pour in liquid formula into the IV bag, which is going to supply them with their nutrients. Once this bag is filled, we have 2 buttons over here, an up button and a down button. They're going to press the up button, and then the bag is going to go up so long as they hold the button. As you can see here, once it reaches the top, they're going to let go of the button, and the gravity dripped formula is going to flow into the gastrostomy tube. Once this bag is empty, we can soon lower it down. From here, the patient can fill it with water again and then raise it up again to flush the bag out and make sure everything's clean. And another cool thing about this device is when you're pressing the up button, the red light turns on. And then likewise, when you're pressing the down button, the green light turns on. And when you're not pressing any buttons, there's a red light here indicating that the device is powered. So this is our gastrostomy assisting device, and we hope you like it. Thank you.
Now that you saw our final prototype, here are the steps we took to get there. We started with an hourglass mechanism, as demonstrated by Figure 1. After that low fidelity prototype, we moved to using PVC pipes to create a medium fidelity prototype. Unfortunately, during testing, we realized the mechanism required too much torque to lift the bag. Therefore, we moved to a pulley prototype aimed at reducing torque, as you can see in Figure 3. We ultimately abandoned this prototype because we found a high torque motor capable of lifting the bag with a winch mechanism shown in our final prototype without the need for a pulley. Now I'll jump into a breakdown of our final prototype, starting with the frame. We use 80-20 aluminum rails because of the high strength to weight ratio and the slots that can be used for easy mounting. However, because of the height of our final prototype, there is still some sway when lifting and lowering the bag, but does not compromise the mechanism. We also attached 4 wheels to the bottom of our frame to make the device much more portable. In the image to the right, you can see the joint we used to attach the frame together, which was successful in keeping the mechanism together. Now Fong will talk about the motor.
Within our final solution, the motor is the muscle of our device. This gear motor rotates a rod with high torque and winds up rope to lift a 1-liter bag. It is also encased in a 3D printed box in order to prevent water damage and exposure. In our final solution, our user interface is controlled by 2 buttons on our Arduino control motor. The final user interface raises and lowers the attached bag. Each button signals an LED to tell the user it's working. The box is encased in a clear acrylic case in order to be water resistant. Foam is also underneath the buttons for further water resistance. Underneath the base of the box are screw holes so that it can be mounted to the metal frame. The user interface uses an Arduino and PCB board to help program a motor driver to control the motor to do certain functions, as well as put in response LED lights. Seen in figure 1, it is powered by a 12-volt power supply, which is then split to power both an Arduino and a motor driver. The Arduino uses buttons to signal to the motor driver what to do with the motor, and the motor driver actually controls the motor. In figure 2, keycaps go above the buttons to give the user easier access to the buttons, and it is labeled to tell what the buttons do. We tested our final solution in a number of ways. Many of our tests use a user-defined scale, or UDS, from 1 to 5, where we get the input of the users from our results. We tested each of our critical design criteria. For ease of use, our most important criteria, we had 15 people raise and lower the device twice and got the responses for how easy it was to use. For maintenance tests, we had each participant also fill the bag before raising and lowering the bag and had their response. Our test for portability, we also had 15 people move the device on a set distance and rate how easy it was to maneuver. And for our final test of water resistance, we squirt 1 bottle, or approximately 16 fluid ounces of liquid, over the machine and saw if there were any breaches of water or external problems. Long will now explain our results from these tests.
Following our testing for ease of use, easy maintenance, and portability, we received our results back. We had tested these criteria within our design team, our peers, and our client, Sue Steves. The results showed that all of the user-defined testing passed the set criteria of averaging 4 or greater on a scale of 1 to 5. The ease of maintenance and portability both scored 4.8, while the ease of use testing scored 4.67. In regards to our water testing, following 1 spraying with the bottle, we found that water had gotten inside the acrylic Arduino box. We decided to stop testing as any more water could have potentially damaged the device, and we considered the test a failure. Although that test was a failure, overall our design was functional. It was able to lift a 1-liter IV bag to the appropriate height with it fully filled at 1.5 kilograms in weight. The device was also portable, easy to use, and easy to maintain. However, there are limitations to our design. It is not necessarily wheelchair accessible, as the bottom bar of the frame and the wheels makes access difficult. The buttons are also too small for individuals with muscle weakness, as is the case with ALS, where they lack those fine motor movements. And as noted earlier, it failed the water resistance test, which is important when dealing with moving liquids. With that being said, future work to be done on the device consists of a high-fidelity mount for the Arduino that is watertight with buttons appropriately spaced and sized. There will also be limit switches which automatically shut off the motor when the IV bag reaches the top or bottom of the device so it doesn't flip over. Addressing the accessibility issue for wheelchair users, instead of a rolling frame like the one we have right now, a table mount design will be used for ease of access. And finally, we would like to thank Sue Steves, Professor Caves, Dr. Rourke Horstmeyer, Jackie Herzberg, Dr. Cameron Kim, and Ali Stocks for making this project possible and supporting us every step of the way.